Next, we'll discuss the third and final topic that we need to discuss regarding ceramics. And that topic has to do with refractoriness, which is the property of having a very high melting point. And ceramics are much more refractory as a class of materials compared to other types of materials. And as I mentioned once before, the high melting point really limits our options for processing the ceramic materials, getting the material into the shape we want it to be in so that we can use it in the end. And that's what we'll talk about in this third section. So the difficulty comes in that if we want to process a metal and get it into a shape, or a polymer material, then we would typically melt those materials and cast them or inject them into a mold and very quickly, economically get them to take the shape we want. If not, then we still may be able to stretch metal or a polymer material, push on it, punch it to get it to take the shape of a mold, roll it or draw it out into the shape we want, possibly with some minor heating to accomplish that or relieve stresses that occur during those processes. But we can't do that to ceramics either, because they don't plastically deform. Those dislocations can't move within the ceramic crystals. And so the properties of hardness and high melting point that are so advantageous to ceramics in some applications become real hindrance in getting them into a new shape. And so how do you take a block of material that's hard and can't be melted and get it into another shape? You do that by grinding it into a powder and then rearranging the powder particles to be in the shape that you want them to be in. And the problem that occurs is that we talked about earlier in the class packing factors, and you know that if you have some particles that are rearranged and packed back together as efficiently as they can be, that there will still be some empty space in between these particles. And so then your ceramic that's been reshaped is very porous, and you need to try to eliminate the porosity or fill in the porosity some way. And so that's powder processing, when we grind the ceramic into a powder and then reshape it. And typically that powder will be included in a liquid, sometimes called a slurry, sometimes called a slip. And that liquid is going to be shaped in some way to form a very fragile object that has the shape that we want it to have, and needs to be fired or sintered in the furnace in order to make it stronger. And so that fragile object, after reshaping the slurry or slip, is called the green body. And then we fire that in the furnace and densify it as much as possible, and then it's called the white body after that. And the white body is the final ceramic product that we will use. So what's in this slurry, this powder suspension? Well, we of course have the ceramic powder in there, and then we'll have some type of liquid. Usually the liquid can simply be water, and we have to have a binder to get the ceramic particles to stick to each other once we press them or cast them into the new shape that we want them to take. And so that binder could be clay, is the really inexpensive alternative. But if we want to make a product that's quite strong and has certain aesthetic properties, then we may need to go a more expensive route and use polymer instead of clay. And then we also, if the slurry is going to be injected into a mold or pressed into a mold to take its shape, we'll need to have some type of lubricant included, and that could also be a polymer material in the case of more expensive products. But in the case of an inexpensive product, clay is a nice alternative because not only is it a inexpensive material, but the same material can be used as both the binder and the lubricant in those type of applications. Dentistry counts as a high-tech application, and so we would use a polymer binder and lubricant in our slurries. Okay, so how do we get the slurry into the fragile shape that we want it to have the green body? We have three common methods of doing that. That's by vibration blotting, pressing, which can be done at room temperature or in the furnace at high temperature, and slip casting. And the method that we use will control the porosity, the flaws in the final product, and that will control the strength, and it will control the possible amount of opacity that we'll have in the final ceramic. And then if we have a lot of porosity, we will need to try to eliminate that. And if you have a lot of porosity, it may be impossible to fully eliminate it, and you'll end up with a porous white body. Okay, so first let's look at an illustration of what vibration blotting entails. That is where you would take a slurry. In the case of vibration blotting, the slurry is a very thick, fairly dry slurry. It has a consistency that is sometimes referred to as a beach sand consistency. Like when you go to the beach, the sand that the water has recently touched and then receded has a moist appearance to it, and it'll feel solid under your feet. But then if you make a rhythmic motion by tapping your foot on the sand, the mixture of sand and water that's there will become watery. And the same thing happens to this slurry. And that's why we call it vibration blotting. And so an artist brush can be used to pick up this slurry and deposit it onto the shape that we want it to take. And we can make layers with various colors, and then use tapping by hand or a vibration platform, and that will bring cause the particles to flow together and pack more tightly and cause the excess liquid to rise to the top, and it can be blotted off or absorbed with some towels. And in case you are looking at this figure and thinking to yourself, wow, those teeth, the crowns of those teeth look very rough and the gums are very large. Why did someone make a prosthesis that looks so ugly? Actually, that is all porcelain. That's all going to be part of the crown of the tooth in the end. The pink part does not remain pink after it's fired in the furnace. The white part will not be so opaque white. It'll turn more translucent. The colors are color-coded for the degree of opacity that the different types of ceramic material will have after they are sintered, become a white body. And they're colored with food dye type chemicals that burn off in the furnace or decompose to lose their color. Okay, so the second method that we mentioned for shaping a slurry is pressing. And we call it cold pressing if we press at room temperature and then pack the powder slurry into a mold. put a cap or a plunger on top of there and apply some type of force at room temperature, and then remove the object from the mold and place it into a furnace. Draw a furnace for you there. And heat that. And so that would be cold pressing. If we press it at room temperature and then remove it from the mold to put it in the furnace. In hot pressing, the pressing occurs inside the furnace. So it is sintered and pressed on simultaneously, and that requires a very expensive type of furnace, so it's rarely used. Now we have two methods of accomplishing the pressing. One is called uniaxial pressing, where we just apply pressure from one side and make the plunger a little bit deeper so that it packs the powder into the shape that we want it to have. And the problem with using uniaxial pressing is that afterwards in your product there is a gradient of packing densities, and the parts that have more porosity left in them will shrink more upon sintering than the parts that have a little bit of porosity left in them, and that will cause the part to warp and it won't fit wherever you want to put it afterwards. And so we have a better method we use when possible called isostatic pressing, where we put a rubber jacket around the material and then we inflate the rubber jacket with water, hydraulic pressure, and it applies pressure equally to all parts of the material and results in fewer compaction gradients and less warping upon sintering later. And this is the method, incidentally, that's used to make CAD/CAM milling blocks for dental ceramics. CAD/CAM for milling. Computer-aided design, computer-aided machining is what CAD/CAM stands for. And you can see an example on the lower right of some diamond burrs controlled by a computer, whittling away unwanted portions of these blocks and leaving the shape of a ceramic framework for a crown or a fixed partial denture. The third method that we use to get a slurry into a shape is not the best method for getting a precise shape or a strong material. It's used nowadays mostly for artistic ceramics. Used to be used in dentistry, but it's not so popular anymore. And this method is called slip casting. And in slip casting, you will make a mold, and the mold will be made out of some ceramic material that has tiny pores, network of tiny pores in it, and then you will cast your slip. Usually this is a very watery slip in this case, and you will cast that into the mold, and then the pores on the wall of the mold use capillary pressure to suck up the water from the slurry, and that results in the powder particles in the slurry being compacted against the walls of the mold. And then the excess slurry is drained out of the middle of the mold, and it leaves a shell lining along the inside of the mold. The mold can be split apart very gingerly, and then you get the green body, which can be fired to make it stronger. However, this method results in a lot of residual porosity in the material compared to other methods, and usually after slip casting, this porosity cannot be entirely eliminated by firing, and it has to be filled in with some other material. An example of how that is used in dentistry would be using a elastomeric impression material, rubbery type material, to take the shape of the crown preparation in the patient's mouth, and then casting a absorbent material into that rubber mold, letting it harden and removing the absorbent material, and then using this as a mold that we then paint the slurry, in this case, on the outside of. It's difficult to see because both the slurry and the mold, the positive replica that we've made, are both colored white. But we paint that on the outside, and the positive replica of the crown preparation will suck in the water and absorb it from the slurry. That can then be fired and removed from the surface. Makes a shell in the shape of the framework of the crown. And this has a lot of residual porosity in it. So in the case of this product, a glass powder is made into another slurry, very watery slurry, and painted onto the surface, and then melted, and capillary action, again, in this case, causes the melted glass to wick into all the unfilled pores and fill that empty space in. Unfortunately, in our test results, it seems that about 5% of the specimens do not have the glass penetrate entirely, and so there's some large porosity left in the middle of the product.